The sample correlation coefficient, R, is the measure used by statisticians to determine the existence and strength of the linear relationship between the dependent and independent variable. One of the characteristics of the coefficient is that its values is always between -1 and 1. -1 being perfect negative correlation and 1 being perfect positive correlation. The magnitude of R indicates the strength of the relationship. So generally, a value of between minus 0.6 to negative 1 and to positive 0.6 to positive 1 indicates strong relationships. The sign of R indicates the direction. If R is greater than 0, the direction is positive and the line is slanted this way, so it forms an acute angle with the positive direction of the x-axis. And we say that there is a positive linear correlation when the variable x increases, also the variable y increases. An example of that is, for instance, the age of children and the corresponding height. Age being our x and the height being the y. When R is less than 0, then the correlation is negative and the line is slanted the other way. And this is a relationship where the variable vary in opposite direction. So an increase of x corresponds to a decrease in the corresponding y. And a good example of that is if x is the age of a vehicle and y is the resale price or resale value. When R is close to 0, it generally means that there is no linear relationship. So the points are scattered in the scatter plot. The points are scattered a little bit all over the places. Also, it could mean that there is a relationship, but it's a nonlinear relationship, such as a logarithmic relation or a parabolic relation, or so on or so forth. The other important thing to note for R is that there are no units, and also R is not affected by changes in the scale of either variable. Those are all characteristics of the correlation coefficient. Population correlation coefficient is a parameter which is called ρ. Is the Greek R, and this is for the population correlation coefficient. There are various formulas for the correlation coefficient, and they are all algebraically equivalent. The one that I like most is this one that is written here at the top, where it says that R is equal to big fraction line and then sum of the products xy minus fraction line sum of the x's multiplied the sum of the y's divided by n. And the denominator is basically a known quantity because it's the square root of the product of. This is, I don't know if you recollect, this is the numerator of variance. So it's being under root is like the numerator of standard deviation for variable x multiplied the numerator of standard deviation for the variable y. An equivalent formula, if we find the common denominator, both in the square roots and everywhere, this becomes equivalent to this formula here, where this n sort of precedes the sum of the products xy's, and then is disappeared in here, and then this n precedes sum of the x squared and the sum of y squared and disappears from that. And also there is another equivalent formula, which is so a little bit similarly to the computing and reasoning formulas for standard deviation. This one is sort of the computing formula for correlation coefficient, and this is more like the reasoning formula. And this is the sum of the products of the deviation. So this is the deviation of the variable x minus x bar, and this is the deviation of the variable y minus y bar, and they are multiplied together, and then they are added. So for each pair. and then divided by, and at the denominator we have sort of the variance, the standard deviation, the sum of the square deviation for x under root, and multiplied by the sum of the square deviations for y. We divide by n minus 1, this would be the standard deviation of x multiplied the standard deviation of y. And if we divide this numerator by n minus 1, which all simplify, so the n minus 1 are gone, the numerator of this formula changes this way. So now, another way to write it is Sxy, meaning the sum of the deviation of x times the deviation of y. So this guy, the numerator without the n minus 1, is called Sxy, and the denominator is the root of Sxx times Syy, and Sxy is defined in here. So the sum of the deviations of x multiplied by the deviation of y for each pair, and then Sxx is the sum of the square deviation of x, and Syy is the sum of the square deviation of y. This is sort of easier to recollect. And then we want to see a little bit of the reasoning. The reasoning in here is that basically once we have the scatter plot of the data set, so we could have a scatter plot of this kind. So what we do for every observation, we standardize it, we sum, we add up. So we standardize the x observation, so this is the formula of the z-score. The formula of the z-score is x minus the mean over the standard deviation. So in here, if we do it for the variable x, it becomes data minus mean over standard deviation. For the variable y, is data minus mean over standard deviation. So it's like find the scatter plots in standardized form. Standardize the observation, removing the units of measurements, and then the scatter plots gets centered at the mean x by y bar, and the variables are the standard deviation units. So this is how we get to the formula. The formula for the sample correlation coefficient is called Pearson's product moment formula, and we can use any of the three versions, but we generally stand with them. I like to use this formula here, and sometimes people use this formula here with these notations here, which corresponds to the formula that is written in red at the bottom. We'll follow up with examples in the next clip.